Chapter 3 looks at matter and energy. So we're going to look at definition of matter, how matter is classified, and then we're going to look at properties of matter a little bit later. So first, let's start with matter. Let's give some definitions of matter. So matter is something that, one, has mass. So matter has to have mass. And the second thing matter has to have to be considered matter is it has to occupy volume or occupy space or have volume. So it takes up space or it has volume. So matter has mass and matter has volume. So we classify matter into essentially two categories. We have a sample of matter that is pure, and we can have a sample of matter that is a mixture. When we talk about pure matter, we can have elements and compounds with a mixture. A mixture can be heterogeneous or homogeneous. So we're going to go through all of those differences here. So the first thing I'm going to do is kind of define what this means. So an element is something that cannot be broken down to a simpler substance. Okay, so it cannot be broken down into a simpler substance. So it's a sort of the simple, most basic form of matter. So I like to think of elements as kind of like building blocks, so kind of like Legos. So here I have a few different sizes. So these are all basic building blocks. I have one that has 4, one that has 6, 1, and 2. So these are all basic building blocks. They're all just slightly different. And that's the way elements work. Some elements are very, very small, like this piece here, and you can have some elements that are very, very large, like say this Lego block here. They're all basic building blocks. The only difference that we're going to see in chapter 4 that makes one element different than the other is essentially kind of the size of the atom. Okay, so these are elements, these are our simple building blocks. Okay, so let's look at some examples of elements. So some examples of elements could be something like iron, which we're going to learn in chapter 4 has the symbol Fe. Something like oxygen. Oxygen as an element exists as O2. We're going to talk about that in chapter 4. Some elements exist as pairs. We call those diatomic. Some of them exist together as one. Or, I don't know, how about sodium, which has the symbol Na. So even though we won't officially talk about this until chapter 4, you can find all your elements on a periodic table of elements. So when you're doing the sort of homework for this chapter, when you're asked to classify something as an element or a compound or something like that, your elements are going to be found here on the periodic table. So these are our building blocks. So our very small one, like our hydrogen, would be like this Lego here. And then you have much larger things, say like lead, which would be sort of these ones down here on these sides. So our smaller ones are here, our larger ones are here. If you see any of these listed by themselves, these are elements. And again, we're going to talk about this periodic table in more detail in chapter 4. Okay, let's move next. Next we have things called compounds. So a compound is 2 or more elements combined in fixed ratios. Okay, so 2 or more elements combined in fixed ratios. So it'd be like taking one of our blocks and then, here, actually I want to use this one, taking one of our blocks and combining it with others. So here I've taken one green block and combined it with 2. And I did it in a fixed ratio. So I have one green block and I have 2 white blocks here. So this is sort of my representation, for example, of water or H2O. So we have 2 hydrogens and 1 oxygen. Okay, so we have them combined together. So again, in the Lego world, I've attached them together. We could also have something like sodium chloride. So sodium chloride, which is NaCl. So 1 sodium and 1 chloride that we've combined together in that fixed ratio of 1 of each. So my water, and I have my sodium chloride here. Just for, another one to have 3 examples. Carbon dioxide, CO2. So again, something like a carbon dioxide. Oxygens are a little bit bigger than carbons. I don't know, so maybe something like this. A carbon with my 1, 2 oxygens, so CO2. So something like that. Okay, so it's not exactly we'll talk about how these really combine and things like that as the chapter moves on, but kind of as a simple picture, this is what's going on. Okay, so I want to kind of expand on this. When we talk about pure, we talk about only one type of element or compound present. So a sample would be pure if there's only one type of that element or compound present. So for example, if I had a sample of sodium chloride, all of them would look identical. So our sample of sodium chloride would all have just the same ones present. Okay, so this would be a pure sample of sodium chloride, where just that is the only thing present in that particular sample. Okay, so that's pure. Or if it was, for example, our water, again, it would just be only this type of compound would be present. Okay, so they all are identical. That is pure. Okay, so kind of before we move on from compounds, kind of want to expand a little bit more off of that. When a compound forms, a compound always forms with the same mass percent of each element. And this is the law of constant composition. So we're going to talk about this a little bit more as we move through this chapter, especially when we get into, say, chapter 6. We'll talk about this more. Law of constant composition or law of definite proportions kind of goes with this. So what this means, again, if they form with the same mass percent. So for our water sample, which we know is 2 hydrogens and 1 oxygen, so they're always the same, 2 H's, 1 O. And also, when it forms, the mass percent is the same. So every single sample of water is 89% oxygen and 11% hydrogen. So every single sample of water has that in common. So knowing sort of this here or having these observations is what led scientists to believe in sort of these building blocks or these elements here, that's how matter was sort of set up in this here. So this was something that scientists could measure very early on, and that led to sort of the idea that we had all of these elements out there and that we could put them together just like Legos. Okay, so now we're getting to the other side here, our mixtures. So we have heterogeneous and homogeneous. So let's look at a mixture. If we were to define that, a mixture is 2 or more elements or compounds are present. Okay, so there's 2 or more elements or compounds present in that particular sample. Okay, so we have 2 types. We have heterogeneous and we have homogeneous. So hetero means different. So this is just non-uniform. So when these sample forms, you can see distinct layers. So for example, if we had here we'll go with elements. So for example, if we had oil and water, they form non-uniform. What that means is that my water, so in this example, these little orange Legos are going to represent my water. So my water would be one part of the sample and my oil would be at the other. Okay, so very, very distinct layers, non-uniform. All of one compound are here, all of the other are up here. So we didn't have equal mixing together. We had very distinct layers where we could see that there's a difference there. So non-uniform. Okay, so some examples, sort of the one we just saw, would be like oil and water, where again you form those distinct layers there. Let's see, something like granite. If anyone has like a granite or rock countertop like that, you can see different patches of different color moving through the rock, where you have different mineral composition throughout the rock. So something like granite, again, not uniform. And then, I don't know, how about a taco? Taco, also heterogeneous mixture. You have your shell, you have your meat, you have all that sort of thing. So heterogeneous mixture here. So hetero means different, homo means same. So here we form a uniform mixture. Is a non-uniform and uniform here. Okay, so forming a uniform mixture, now let's say we, instead of having oil and water, now let's say we had salt and water. So if we had salt and water, we would have a very uniform distribution of all of our parts of our solution. So when it was oil and water, we had oil together, water together, separated out. Now with salt and water, we have a nice even distribution or an even mixing of the two. So we have a uniform mixing where everything mixes together. So homogeneous mixture, we don't really use that word a whole lot. We have a shorter word for that called solution. So you'll probably see that a little bit more than homogeneous mixture. So a homogeneous mixture is what we call a solution. Okay, so there's a lot of really important ones. We're going to kind of throw some of them out there. Alloys are homogeneous mixtures. So alloys are things like brass and bronze, etc., steel, so on and so forth. Okay, so those are alloys. So those are homogeneous mixtures of metals. So for example, brass is a mixture of zinc and copper. You melt them down, you mix them, they reharden into this mixture of metals. So that's an alloy. The one we just saw an example of, salt water. Okay, so that forms, when they mix together, it forms a homogeneous mixture where the salt is equally or evenly distributed through the sample. And another one we have is air. So the air we breathe is a homogeneous mixture of nitrogen gas, which is N2, oxygen gas, which is O2, argon, carbon dioxide, and some other trace amounts of gases here. But equal, even distribution of gases in our air. Okay, so those are homogeneous mixtures. So something I kind of want to look at is a sort of distinction between them. When you get into the homework and things like that, it's going to ask you if is it an element, compound, or some sort of mixture. So elements can be found on the periodic table. So if you can find it on the periodic table, you know it's an element. Compounds are generally named based off of the elements. So water, that's the common name. This is really called dihydrogen monoxide. So it has the word hydrogen and oxide or oxygen in it. This you see its name is sodium chloride, kind of indicates that there's sodium and the element. It ends in "ide", but chlorine there. We have carbon and oxide, which is oxygen. So generally speaking, your compounds are going to contain the names of the two or whatever elements you have in there. Okay, so your mixtures, again, a lot of times you're going to have, you'll have to kind of know what the thing is to allow you to figure out what it is. But if you don't know, for example, what granite is, it's really easy to look either in the book or a quick internet search would give you a picture of what that looked like, and you can see if it was a heterogeneous or a homogeneous mixture. Okay, so one other thing, going back, like a compound. A compound can be decomposed. So element cannot be broken down. This can be broken down. We could take our water and we could break it down into its elements. We could separate the oxygen and the hydrogen out. So that's essentially the difference between, again, those two. The element is in its sort of basic building block. Our compound, we again, linked some different elements together to make this compound, but they can be broken down. You can always break a compound down into its elements. It takes quite a bit of energy to do this. Okay, so it's not something that a lot of times naturally happens. You have to put a lot of energy. And for example, to do this with water, you have to run quite substantial current through the water to get it to break apart into the oxygen and the hydrogen. Mixtures, on the other hand, are pretty easy to separate the components. So because I didn't actually link any of these things together, so when I had my mixture, like my heterogeneous mixture, I just had everything sort of by itself, sort of free floating. These are easy to separate. So if I wanted to separate my oil from my water, all I would have to do is pour the oil off and leave my water behind. So those are generally easier to separate. Like your taco, you can take all of the components out. Even with granite, you can do some of separating of things also. So again, generally speaking, these are pretty easy to separate. These ones are also easy to separate as well. Like for example, our salt water. So our salt water, where everything is mixed in evenly here. To separate like a salt water mixture, all you would have to do would be heat it. So put it on the stove, heat it up. The water is going to boil away and leave your salt behind. So mixtures are easily separated by, generally speaking, some easy means. A compound is not that way because you've actually formed chemical bonds there. And we're going to talk about that, in the chapters to come. But again, when I made this compound, I linked these Legos together. So much more difficult to separate.